Arben Pitarka is the seismology group leader at the Lawrence Livermore National Laboratory, where he has been working since 2010, and he has a strong background in computational and engineering seismology. He received his Bachelor of Science in Geophysics from Strasbourg and completed PhD in computational seismology at Kyoto University, Japan. During his career, Arben worked as a research seismologist at various institutions, likely being BAI, it's the Macroni Electronic System and British Aerospace Corporation, and the Air Force Technical Applications Center in Florida before joining Lawrence Livermore Laboratory in California. He has extensively contributed to the development of physics-based earthquake rupture models and hybrid techniques for broadband ground motion simulation, especially for engineering applications. Additionally, he is directly involved in nuclear explosion monitoring techniques for understanding seismic wave generation during underground chemical explosions and developing seismic source discriminants. He's involved in various collaborative research projects with organizations such as Japan Nuclear Regulatory Authority, U.S. Nuclear Regulatory Commissions, U.S. Department of Energy, SCEC, Grenoble University, and INGB. I think I said everything. I'm done. So please, Arben, welcome to you again, and go ahead with your presentation. Thank you.
Okay, thanks, IBG, for the introduction, and thank you everybody for attending this seminar. I will try to be brief because the time is very limited, and our objective was to just give an overview of the physics-based ground motion simulation techniques that we're using, and which has been also the subject of a very, I would say, productive collaboration with your institute that started, as IBG mentioned, a couple of years ago, and we are now in the phase where we're kind of exploring the next steps after installing the technology in your computation capabilities. So the content of my talk will be focused mainly on explaining a little bit what is the broadband ground motion simulation methodologies that we're using, talk a little bit about the kinematic rupture constraints using dynamic rupture modeling. We will show a little bit of the performance of 3D models that we are using with stochastic variability in some of our test sites. I will show some examples of simulations on high-performance computing platforms and how we validate those ground motion. And I will briefly introduce at the end, if I have time, the large project that we are working on, which is called Earthquake Simulation on GPU-accelerated computers, which has been really successful and is a bridge between the seismology and engineering community here in the United States. So why we need simulations and why they have to be high frequencies. As you know, in the United States, we have a big seismic hazard mapping. And on the left, I show the seismic hazard map. And we do have recorded data that have been used to generate those maps, but they're not enough. And unfortunately, some of the DOE sites, Department of Energy sites that are very important, are located, those are shown by triangles. They're located in areas where the seismic hazard is extremely high. And the other thing is that just recently we are trying to reevaluate the earthquake resilience of new energy missions and DOE, and that include a lot of nuclear power reactors of various scales, but also new energy programs, and those all needs some seismic hazard evaluations. The other thing that is mostly important is that, as you know, in developing ground motion models, even in Italy, for instance, we have lack of data at shorter distance and for large earthquake, which is shown on the left. On the right, we also show that there is a urgent need to complement our databases with recorded motion with synthetic motion at very short distances. You can see that several ground motion models that have been proposed for Western United States, they vary a lot at distances that are shorter than 5 kilometers. There is a discrepancy there because there is no data, and so there is a factor of 5 between them. So at least we acknowledge that we need simulations to close that gap. So everybody is now familiar with the terminology that we are using that we call broadband earthquake ground motion simulations. But what are those? They fall into 3 categories. The first one is what we call the ones that are using a deterministic approach, which I'm going to talk today. And usually, because of the computation capabilities, that may be used maybe up to 10 hertz. Then there is a stochastic scheme that they are kind of older in the sense that they have been around for a while, and they use a stochastic approach. You can use them for maybe high frequencies also. And the most popular are the hybrid approach schemes, which are based on the deterministic ground motion modeling up to usually 2 hertz, 1 hertz. And then they use stochastic ground motion representation at higher frequencies. Like I said, this is the most popular scheme because it's kind of cheaper than the deterministic approach. But I think that the deterministic approach is the future, as I will show the computation power is increasing exponentially. But for all these techniques, the basic step is, and the most important, is the generation of a kinematic rupture model. And for that, we use our empirical knowledge that relates the magnitude with some general characteristics of a rupture, which is the rupture area, fault geometry, fault mechanism, and the rupture initiation. But then we add our physics-based modeling based on dynamic rupture modeling and inversion of real earthquakes to actually predict the slip distribution, the rupture initiation time, and the slip rate function. All these 3 parameters are extremely important because, as I will show, they control the level of the ground motion. And then on the right, I show a general scheme how we work. So once we get the rupture model and the material model, you use any numerical scheme. In our case, we use finite-difference method, but finite element and boundary element methods are very popular. And you come up with a set of synthetic ground motion at important locations. So in our physics-based modeling, which is based on high-performance computing, we have been using 2 important codes. The one is shown in the left is what we call the rupture generator, which is based on a already validated method, and it's been very useful in generating ground motion, in generating rupture models for several years at SCEC and also in my institute. And that is under development. The other code that we're using is the SW4, which is a fine difference method based on a techniques that were developed in my lab, and it's a curvilinear mesh with grid refinement that is very suitable for modeling complex 3D structure and topography. The other source, the other improvement of our modeling scheme is that since we're now moving at very high frequencies and the knowledge of the geology is not at the level where we have this kind of high granularity in our model, we have to rely on stochastic geology. So we kind of develop some kind of schemes that are helping that direction. And then the next step is running those simulations in our computation platforms, and one of them is LASEN. And to give you an idea for what are the requirements for ground motion simulation in the Bay Area here in San Francisco, we need at least 5,000 to 7,000 CPUs and a wall time of 5 hours to generate ground motion for a magnitude 7 earthquake on the Hayward Fault. So let me talk a little bit about the kinematic rupture model. As I mentioned, this is one of the main engines in our simulation scheme. We start with a kind of semi-deterministic slip distribution that is based on technique that were developed a long time ago by Martin May and Barossa, that gives us a overall slip distribution on a broad range of wavelengths. And then we tie in now, once we decide where the rupture will initiate, we tie in the rupture time. That means that when, how the rupture will propagate across the fault is based on the technique that we develop based on observations that rupture velocity that connects to the rupture time is variable with depth. So we assume a 80% local VS for the rupture velocity for depth below 8 kilometers. We slow it down for depth below 5 kilometers, and in between we use some kind of interpolation. But most importantly, what I show here in the middle panel is that we do assume that there is some kind of very high variability in the rupture time, and usually the rupture time accelerates as it goes in areas what we call high slip areas or high stress drop areas. On the right side is also one of the most important parameters that we use in our rupture models, and that is constrained by several studies that were performed using rupture dynamics, and one of them is by Tinti, which probably who has been very active, and maybe everybody knows in your institute. But we also have some other new research that were performed by my colleague Rob and myself. And so we came up with a slip rate function that is consistent with rupture dynamics, and its duration changes also with depth. And I show that there is some relationship with slip, which means that as you move deeper, you tend to generate higher frequencies, and as you move shallower, you tend to suppress the high frequency generation and allow only long period ground motion generated, which is consistent with observation, and I'll show that how. So if we want to visualize how the rupture generates and propagate, I have an example for a recent earthquake in Albania in 2019, and as you can see, the rupture generate a slip background, which is shown by the red, and the blue is the slip rate, which accelerate and decelerate depending on which area slips has a higher slip. So this is a kind of animation that helps us to actually understand how the energy is distributed in time and space. Now, as I mentioned before, this engine is extremely important. So we need to use some kind of physics-based constraints on how the rupture propagates, what is the speed, how the slip rate function will look like, and how its spatial distribution and its shape. And we use dynamic rupture modeling of previous earthquakes that are recorded, and we're lucky to have some of them. I'll mention Lander earthquake, Parkfield, which was very well recorded in California. Recently, we had Kumamoto earthquake, Miyagi, Iwate in Japan, and the recent one, which is the Ridgecrest earthquake. Those earthquakes were, excuse me, very well recorded. As you can see on those three maps, there were some nice distributions of stations. And so what we do, we start with coming up with a dynamic rupture model that can reproduce the slip distribution and also the recorded motion at near fault. So this is one example for a magnitude 6 earthquake. In those models, of course, we need to start with the stress distribution, which is shown on the left. You can see that the stress drop is higher in the high stress drop areas, but if you make a cross section of the stress drop, which is shown on the panel on the left, you can see that we have to assume that the stress drop is very low near the free surface and increases with depth. It does have a jump along the asperity, and then it drops again to a negative value in the ductile part of the crust. So this is a very important assumption that has been working very well in terms of modeling ground motion for earthquakes. And then the other parameter that is very important for this modeling is the d sub c, which is called slip weakening distance. That if you look at on the right side, we use a linear friction law that connects how the rupture dynamics evolve in time, but also in space. The triangle, the green triangle, is what we call the friction energy. And as you can see, that friction energy is controlled by the d sub c and the stress drop. So that means that if you increase the d sub c, then the rupture takes more energy. So that means that it reduces what is called the radiated energy. That means that if d sub c is high, as you can see on the left, near the free surface, then you create some kind of a weak zone where the ground motion has less probability to generate high frequency energy. And so you maintain that weak zone up to maybe a depth of 3 to 5 kilometers, so that the rupture produces the right amount of energy. And then we put this input of stress drop into a staggered with finite-difference method and run the dynamics along the fault. Usually we assume a planar fault, but the code may allow segmentations of the fault. And then you recover the time history and the slip distribution on the fault. So in this case, I'm showing the magnitude 7.1 Ridgecrest earthquake. We use an iteration method to actually come up with a stress drop model that at the end will reproduce the recorded motion that is on the left, on the right, and the target slip distribution that was observed through inversions. So we do start modifying the initial model, which is shown on the left, so that the stress drop distribution and also stress amount will create a slip distribution that is which is shown in the bottom, which is exactly the same as the one that is observed. So once we stop this iteration, which usually takes up to 5 or 7 iterations, we come up with a slip rate function. The slip rate function, as I explained before, is one of the most significant parameters of the rupture kinematic. So now we switch from rupture dynamics to rupture kinematics. So we get in every single point on the fault, we get the time history of the slip rate, which I have shown on the left. On the left, I show a vertical cross-section of the slip rate on the fault at an area that is right in the middle of the fault. But as you can see, that there is a strong variation with depth. And there are 3 typical areas that I show here of the source function. The top is very near the free surface. You can see that it's pretty much a very long period energy that is generated there. And then the middle one is related to the high stress drop area. It is a very nice shape of what we call a Kostrov type. And as you can see, it has a very fast increase in amplitude at the beginning, which is where the high frequency energy is coming from. And then it drops gradually, which also affects the long period ground motion and total displacement. And at the third one in the bottom is what we have in the background. So you can see from there that mostly the high stress drop areas are the ones that actually generate the high frequency ground motion and part of the long period. But the ones that are contributing to the long period ground motion, which is also significant, are the ones that are is the background part of the fault, and also what we call the weak zone, which is usually between 0 and 5 kilometers. So these are constraints that actually were used to develop our rupture generator and improve it as we get more data for earthquakes. So we came up with a analytical form that everybody can use when they produce a kinematic rupture model. Those are very simple forms, but they are very similar to what it was observed for rupture dynamics. On the left, I show with red is the slip rate function that should be used for a high stress drop area. And then in the middle, the yellow color is the one that is in the shallow part of the crust. And then right at the free surface, near the free surface, you get a nice bell-shaped shape function. So we applied to demonstrate how important is this kind of depth dependent of the slip rate function. And we show that here in the simulations of the Ridgecrest earthquake. On the left is the goodness of it, which is the ratio between the recorded and synthetic spectral acceleration for a model that was originally produced. And you can see that the original rupture model overpredict the ground motion. That means that we do put a lot of much high frequency coming from the shallow part of the fault with that model. Now with the new modification that I just showed, that we kind of consider the depth variation of that slip rate function, you get a much better distribution of energy, and then you get a bias which is almost zero between the recorded and synthetic ground motion. So in a sense, there is a lot of discussions of how we can reconcile information that we get from source inversions, which usually are slip distribution that are based on inverting long period ground motion, with models like the one in the middle, which is considering both long period and high frequency energy. And in Japan, we have been working on a project that can merge the so-called Iroquois recipe model, which is based on just a kind of simplified distribution of slip used in strong ground motion prediction in Japan, with what we use now in the United States. And we have been now using what we call a hybrid model that can actually assign by the user areas where we want the slip to be higher. And so this is something that we have been testing, and it has been very successful, and I will show some examples of it. Now, I want to move to another part of the modeling scheme that we're using, is the velocity model. And as you know, it is extremely important. The problem with developing the velocity model is that while we do have a very good knowledge about geology near the free surface, at depth there is less constraint. So we have to reconcile our knowledge with some kind of approximation of the local geology at smaller scale. So recently, there's been a big effort at SCAC and other part of the world to develop models that have some kind of stochastic variability at a small scale. So what we did, we used a experiment that has been developed in our test site, where we lay up a small array of 1,000 seismometers, and we were looking at the cross correlation and spatial distribution of that cross correlation among stations to come up with the a stochastic representation of small scale variability in the crust in that area, which is basically a shallow basin, which is typical in several parts of the world. And here we show simulations based on what we call a geological framework model with stochastic variability for that area. And we show the comparison of snapshot between recorded and simulated. And on the right, we also show the waveform correlation distribution recorded and simulated. So the blue area, it's showing that there is a high, there is a low cross correlation due to very strong wave propagation effects. And as you move away from that basin edge, you have a much better correlation between stations that are 50 meters apart. So that means that there is less effects on the wave propagation. So there is a strong correlation between the local geology with the cross correlation. So we use that cross correlation to come up with some statistical representation of the small scale variability, which we are now have already implemented in our SW4 code. And so this is an example. You can see that I move, from left to right. We have some information about the geology, and then we add stochastic variability to our what we call the stochastic SVM, and that was used in simulation of ground motion from chemical tests on the test site, and also earthquakes, smaller earthquakes. And as you know, in that part of the experiment, we're mostly interested in understanding how the geology affect the generation of different types of waves, how those waves propagates through that structure, and how some of the signatures that we're using in nuclear explosion monitoring are affected by the type of source, in this case, explosion versus earthquake, and also the local geology. So here I show a comparison for a magnitude 3 earthquake, local earthquake, recorded at several stations at the test site. On the left is the recorded, black. On the right is the simulated ground motion, red, for that magnitude earthquake. And you can see that we do a good job with the model with stochastic variability. In the bottom, I show what we call SPF5, which is Source Physics Experiment 5. It's a small chemical explosion very close to the free surface. And as you can see, also for that one, in several stations, the simulation kind of performed relatively well. I don't have time, but I have also figures that show comparison of the waveform fit with and without stochastic variability. And we do find that if you add stochastic variability in a depth that range from 0 to about 5 kilometers, you get a much better fit of overall wave propagation, especially S wave and the Dakota waves. So we use this kind of constraint to come up with stochastic variability in our 3D modeling and also in the Bay Area. But this is a case where we demonstrate how this capability that we have developed can be used for now seismic hazard assessment at our test site, where we have a lot of facilities that we're concerned because there is a what we call a fault that can generate magnitude 6 to 6.5 earthquakes. Although it has not been active, it's still a concern. So we did do a study where we predict ground motion for scenarios. This is a normal fault, and it's a listic fault. It has a complex geometry, and this simulation does show how sensitive is the ground motion to the geometry of the fault, but also to the basin structure. And you can maybe see here in the animation how the waves are generated by the fault, starting from the rupture initiation shown by the star, and how the upward directivity effect generates those really large ground motion that are colored by red. But then you do see that there is a concentration of the ground motion along the fault trace, which is the hanging wall effect combined with the wave propagation effect in the basin. So you see mostly the energy remains trapped in the basin. And unfortunately, there is an area that is close to that triangle where we have underground facility that, because of the shape of the basin there and the geometry of the structure there, combined with some kind of rupture effect, there is a strong amplification of ground motion and a very strong increase in duration. So basically, this kind of simulation can help us kind of predict the level of ground motion in the test site. So I will switch to something that you guys are more familiar, and I would like to acknowledge the collaboration that I mentioned with INGV that we have started several years ago. We did publish a paper, but what I want to mention here is that we have been successful with this collaboration, not just only in terms of demonstrating the capability and how it works for earthquakes in Italy, but also we've been able to transfer this technology, including the Rupture generator, the SW4 code, and now another technique that I'll talk a little bit more that is based on a 1D Green's function. So everything is transferred now in the INGV computation capabilities, and we have been using and testing that for future studies. So for the case of Nocha, for the Nocha earthquake, we were interested to know not only how well this technology can be used to fit the ground motion on a broad frequency range, but also we wanted to ask two questions. And one was how the topography amplified the ground motion and whether it's a repetitive effect, and also what kind of variability you expect for these earthquake types in Italy at location right above the fault or near the fault, how the ground motion connects with the seismic energy and the location of the large slip areas for those type of faults. So the simulations are very helpful to do this kind of sensitivity analysis. And here I quickly go through the geology. I think you're more familiar than me that the structure here is very complicated, and people at INGV, and I want to acknowledge work that Pasquale and Mauro has been doing for developing velocity models. Those are extremely important, as I show. They control actually how the waves will propagate across these very complicated geology. So we do have some 3D models that are shown on the left, on the right, that we use in generating ground motion for Nocha earthquake that are shown on the map in the bottom. And the stations that we use in that study that IBG led was were the ones that are shown with red color. So the other part that we worked a little bit is to come up with a kinematic rupture model for that earthquake. So we use the inverted slip distribution from another study shown on the left, and we came up with a 2-segment rupture model on the right that was used in the simulation. And I would say that for some reasons, either because we were lucky or because the quality of the velocity model and the constraint used in the rupture model produce a relatively good match with the recorded data, which are shown here. These are response spectra at different stations. But in the bottom is what we call is a plot of the goodness of it that shows the ratio between the recorded and synthetic response spectra in the horizontal direction. And as you can see, when the red line it shows the bias of that of the goodness of it. When it's 0, that means that we have a good overall representation of the ground motion. And of course, there is some variability that is shown by the standard deviation, green part of this plot. But overall, the scheme produce really good quality synthetic data. And so we were able to use that data to study what is the effect of topography. And here I show some examples of the comparison between synthetics that we use with topography, which are the blue ones, and without topography, or the flat surface, which are the green ones. And in the bottom, we show also the goodness of it. So you can see with the surface topography, the bias is 0. Now, if we remove the topography, you do have the synthetics are deficient a little bit in high frequencies. So that is something that we are thinking in the current project that we're working on, and I'm going to talk a little bit about that. But on the right, you can appreciate that the surface topography actually does affect the so-called wave scattering, but on the high frequency part of it. Long period, which are shown on the right, which is only flat topography, are still kind of controlled by the overall rupture model and the structure. So The topography, it's some kind of regional effect that depends on the direction of the waves, which direction are they coming from, and the typical orientation of topography itself. So overall, the conclusion was that for some particular site, the topography has amplified the ground motion at the hilltops. But what is interesting for this study is that in terms of predicting the ground motion during future earthquakes, the topography might be a good predictor in terms of where the PGA might be amplified, but not the where the PGV, or peak ground motion velocity, might amplify it, but not the PGA, which is the peak ground motion acceleration. So this study is something that is consistent with some studies that have been performed in the past, that overall suggests that the topography is significant in terms of predicting the peak ground velocity, but the acceleration, which is controlled by high frequency part of the ground motion, it's much more sensitive not only to the shape of topography, but also the local geology. So prediction of that kind of ground motion amplification pattern depends also on the location of the earthquake, not just the shape of the topography. And of course, we can use this kind of simulations at IBGET, produce these plots to actually understand the variability of the ground motion near the source and away from the source. You can see that simulation can guide in terms of how we can produce prediction of the ground motion variability. And this study shows that the ground motion variability is much higher at the source region, and it's shown by the synthetics and the data, and increases or decreases at longer distances based on the complexities in the velocity structure in the area. So these are very important parametric analysis that has to be investigated and included in ground motion models that are going to be refined for central Italy. So I'll move now, and I have maybe less than 10 minutes to introduce you to a DOE project that has to do with using earthquake ground motion simulations on GPU-based system to predict ground motion at infrastructures that are of interest for the energy in our country, but also for seismic safety. So now we have developed a regional scale numerical modeling capability that can be attached to studies of the actually seismic response of sites using models that have been developed by the engineers. So what we are more interested in now is questions like how strong is the ground motion distribution along the fault, and what is the distribution in the seismic demand of the building near a fault. And here I show a case of the San Francisco Bay Area. So as you can understand now, is that the frequency range of the engineering interest is pretty broad, and we're still far away from having a good handling of very high frequencies. But at least using the best computers that we have in our country, starting from 2000 and 2020, you can see that there is a very strong increase in high performance computing capabilities. And here I've shown three computers that we have been using for this project, starting with Perlmutter, which is at the Berkeley Lab, Summit, which is at Oak Ridge, and also the fastest computer in the world, which is Frontier. And we have been able to actually compute ground motion for the Bay Area using these computation capabilities. And I want to show you how important is having a good handling of the rupture model. Here I show in terms of building response. So on the left, I show a animation of ground motion in the Bay Area from a magnitude 7 earthquake on a Hayward fault. As you know, this is the most dangerous fault in the Bay Area, and we expect to have at least a magnitude 7 earthquake in the near future on this fault. Actually, we're due for a strong one. But you can see that depending on where the rupture initiates, in the case top, we initiated from the south, and in the bottom from the north, the ground motion level changes a lot. And on the right, I show the interstory drift for a building that is 12 stories, it's a RC frame. And as you can see, the red area shows a permanent distortion. That means a high damage of the building. So you can see that we can predict now, using this kind of capability, where are the areas where we expect larger ground motion and also large damage to this type of buildings. And we have now already formed a group of specialists to generate a synthetic database for this kind of ground motion, so that engineers can use it for designing buildings in the Bay Area. And here I want to just show you that the red dots, red areas show higher ground motion, at least in the coda part of the waves. And unfortunately, that is the Livermore Valley. That's where I'm sitting. So we are a little bit concerned about that, because even though we are far away from the fault, the simulation does indicate that because of the basin around here, you might have some ground motion. And we have a special program in our institute to actually retrofit some of the buildings based on the simulations. Now, what is the next step? I would like to say that these simulations are now not very expensive if you want to model an earthquake of magnitude 7, which is shown on the left. Now, if you want to move to much larger ground motion, much larger areas that will fit the earthquakes on the Sand fault shown on the right, then you need a very big computers. And this is a test that we did for a simulation of magnitude 7 earthquake on the right for Sand fault on the frontier. And we used half of the computer, and it took almost 10 hours to perform the simulation. So this is a 0 to 10 hertz simulation. It's very expensive, but I think there is a discussion about how far we should go with the simulations, and whether it's worth having a very expensive scheme to model very high frequencies. So the solution is that we may still capture a lot of ground motion characteristics if you go only up to 5 hertz. And those are simulations that can be used by small clusters. And SW4 has been very, very successful. And it's a very efficient scheme to be installed in very small machines. So I would like to talk a little bit about the path forward. And this is actually related with the collaboration that we have with the seismologists in your group. We have already finished the implementation of this computation capability in the INGV platform. It has been working nicely for frequencies up to 2 hertz, and that's because the cluster is not big enough. But at least the technique is there and can be used to start understanding a little bit more about the rupture effects and wave propagation effects. And now we are modeling, I started modeling the Amatrice earthquake, and we're working on the paper. I also would like to acknowledge the work that Pietro Harris and IBGA and me have been doing regarding generating a better platform that can be suited to desktop computer. That means that we may use actually 1D Green's functions, that can go even up to 10 hertz and use very small computers to actually come up with a broadband set of synthetics that can be used for mapping ground motion, for predicting either earthquake during future earthquakes, but also soon after a major earthquake. Now, as I mentioned before, this does not include the topography, but overall, it's a good scheme and it's worth having it. And we have already, Pietro has already installed it, and it's working very well. He has a couple of presentations and maybe a paper coming in. That scheme can be used now to constrain some of ground motion models for central Italy, especially at the near source region, where we expect that it's not the topography, but it's overall the rupture generated that is going to control the variability of ground motion. And then we can certainly try now to understand what will be the next improvement for our geological model or velocity models in central Italy. And I think we will start using this idea of stochastic broadband stochastic velocity in our simulations. And of course, we are very interested to collaborate with the geologists and seismologists in terms of improving our 3D models for central Italy. And we are in the right path because we do have a scheme. We do have a lot of data. We just need some computation time to spend and complete these studies. So I'll stop here, and I'll be glad to take questions.
Okay, thank you, Arben. Aybike?
Yes, I'm here. Thank you, Arben. Thank you very much for the presentation. It was great.
There are some questions or comments from the colleagues.
It seems that everything was clear, Arben. It's good for you.
That's good.
Okay, I think that I can stop the registration, and so I don't know if Aybike want to say something. We are closing